Okay, so the following is true. There is a category of compact Riemann surfaces. Okay. And holomorphic maps between them as morphisms. Holomorphic maps are between them. So this is certainly a category. So I look at the opposite category. This category is equivalent to the category of finite extensions. Finite extensions of this field of C of X. C of X. Okay, so where C of X is this the field of rational functions? It is a field, just like any other field. It's a field of rational functions with complex coefficients. Rational functions over C. And the morphisms are field maps, which are obviously going, the field maps are going to be always injected. The field maps are always injected. And field maps. I mean, so they should be preserving C of X. So this is field maps over C of X. And field maps over C of X. Maps over C of X. Okay. Okay. So yeah. So okay. So this is one of the most beautiful results. I mean, it completely characterizes the category of compact Riemann surfaces and holomorphic maps between them in terms of this algebraic data. This is a purely algebraic data. So this is basically you just write a polynomial with coefficients in C of X. That defines the field. So let me tell you how this goes. So from left hand, so this is an equivalence of categories. Okay. It's not an isomorphism, it's only an equivalence of categories, as we know. So it's an equivalence of categories. So so if you have a Riemann surface on the left-hand side, belonging to left-hand side. So if you have a compact Riemann surface, let me put it this way. Compact surface. So you map it into some C of X in the following way. I mean, into some you attach to this field M of X. So this is the field of meromorphic functions on X. This is the field, at least we know that. Meromorphic functions X. Now, in what sense this is an extension of C of X? So we know that you can prove, although we never proved this, that there exists always, since there always exists a non-constant meromorphic function on X, right? This is one of the most important existence theorem in the whole Riemann surface theory. It's a very non-trivial result to prove, but we assumed it. Meromorphic function on X. So this is F from X to C, or equivalently, you can think of it as capital F from X to C hat, right? So we just think of it as a map into C hat, same thing. So this looks arbitrary. We pick one, and then what you do, you just define this pullback. Consider the pullback map. It goes from meromorphic functions on C hat to meromorphic functions on X, right? But we know what is meromorphic functions on C hat. What is meromorphic functions on C hat? This is just field of rational function. That's what we know. This is C of X, right? Or C of Z. That's okay. So this is here. And because this is non-constant, of course, we know that this is a field map, so this is injective. So this injects this into M of X. And then you can prove results, more or less what we have proved is enough, more or less, to show that this is actually a finite extension. So this is a finite extension. Okay. So this is a finite extension. And so you may complain that, hey, this is not a canonical thing because you just chose a meromorphic function, and if someone chooses another meromorphic function, yes, this is a valid point, but up to isomorphism, this won't change. It does not define a functor, but it basically shows that the functor that I'm going to construct from right-hand side to left-hand side is full and faithful, and that's a kind of inverse to that functor. Basically, that's part of the construction, part of the proof of this statement. So how to go from right-hand side to left-hand side? Let's see that. So this is basically part of the construction, but now from right-hand side. So conversely, if you have a finite extension, let n means C of X to inside n, a finite extension, right? A finite, I mean, by extension, we mean field extension. Field extension C of X, right? Okay, since this is finite, so I can take a generator like Y for this. Y belonging to M, be a generator of this extension.
So the extension is of C.
Sorry.
Are we extending C or are we extending C of X?
Oh, no, we are extending C of X.
Oh.
That's very important. Yeah, exactly. We are not extending C. We are extending the whole C of X, yes. And in fact, over C, this is not finite. Over C is infinite dimensional extension. But the base field is really C of X, field of rational functions in one variables. Okay, so there is this. So then what does this mean? It means that Y satisfies an algebraic equation, right? So Y satisfies
Quotients of polynomials.
Sorry?
Rational functions as in polynomial functions and quotients of
Quotients, yes, exactly. That's the standard good old high school rational functions. Yeah, exactly. So let me get my laser. So that Y must satisfy this. I mean, an equation like this, or so Y satisfies the equation of the form Y n plus P1 X Y n minus 1 plus P2 X 1 minus 2 plus P0 of X equal to 0. All these PIs are rational functions. And you can clear the denominator. If you clear the denominator, then you get something like some coefficient here times this. So basically what it is, I mean, you can think of it as an algebraic curve. Here's an equation of an algebraic curve, right? So this is, and you can arrange this to be irreducible. So we get an irreducible algebraic curve over C. So what you can do then, you can look at its locus. It's a set of solutions in C2, as we did. We did, the first lecture. One. So let basically, I don't know what notation to use, or just this notation takes this to be the Riemann surface, the subset of C2 instead of its solutions. So this is a non-compact Riemann surface. The non-compact Riemann surface. And what can you do? Now there is a theorem you have to prove that any Riemann surface which comes from an affine algebraic curve like that can be compactified by adding a finite number of points. You can compactify into a smooth Riemann surface, by adding a finite number of points. So this is a theorem that I didn't prove, but it is true, and it's not so trivial, but it's not so bad either. So X tilde can be compactified. And this is completely canonical. It's called normalization of the curve, can be compactified. To a compact Riemann surface, to a Riemann surface. And this is more or less a functor that's from right-hand side to left-hand side. And this functor is full and faithful because there is this kind of quasi-inverse I constructed from left-hand side to the right-hand side. So this is more or less the idea of this equivalence of categories. So this is very nice. So, okay, so this is just a sketch I did. So basically, so let me write it again. Here is compact Riemann surfaces. The opposite, of course, I have to take the opposite because in that direction I'm going, I'm taking the field of meromorphic functions. So you're going to the dual so that the direction of arrows gets changed when you dualize like that, right? So this category is equivalent to this category of finite extensions of, C of X. Okay, so roughly that was the steps in the proof. There is another category which looks like this. Then you tell me what that other category is. We discussed this several times with some maybe references to the analogy, but not maybe that much. But do you remember there was another category which somehow comes close to this? And then because this is close to this should be, what is that other category? What's that? No, this is something completely number theoretic. Oh. Yeah, so this is the category. Instead of C of X, you just look at Q, finite extensions of Q. So if you replace C of X by Q, the category of finite extensions of Q are just this space or a set of all number fields. So we have here the number fields, all number fields. So a number field by definition is nothing but a finite extension of Q. So okay, I could call algebraic number fields, but that's okay. So these are a number field is just by definition is a finite extension of Q, field of rational numbers. Now, for example, you have quadratic number fields, you can have cyclotomic fields in the first ones that were studied, and a lot of things. Okay, so this also comes close to this. So basically, they form a kind of triangle. I mean, I'm not saying this is equivalent to this by any means, or this is equivalent to this. But there are some mysterious relations between, or analogies between these things. Similarities between these things. So that's part of the kind of analogy, which is called the Rosetta Stone. Okay, I have to qualify this, so I will add a little more about this. So this is Rosetta Stone of math. So this was actually noticed a long time ago by Dedekind and Weber. They wrote a very famous paper in 1880s. The goal was to write everything Riemann did, well, part of what Riemann did, not everything. Part of what Riemann did in completely algebraic term, and to give a proof. They were successful, and they noticed this analogy back then already, or this analogy, I should say, back then already. But then there is also due to André, which is, there is a famous letter he wrote to his sister. You know the story of that letter, right? When he was in jail. He was put in jail in around 1940s for refusing to join the army to go to war. So he had to spend for a few months in jail. And his sister asked him, "What are you doing?" And he wrote a very famous letter explaining the analogy. So I highly recommend you read that letter. It's a very, very important letter. Okay, so this is called the Rosetta Stone because he made the analogy with Rosetta Stone. I mean, okay, so, but what Way made it clear that instead of number fields, so we should look at function fields over finite fields. So this is a better analogy. So I just write this and then I finish. So I finish about this, I mean. So it's better to take function fields over finite fields. This, I mean, this way the analogy becomes much more precise and kind of more manageable. Function fields over finite fields. So the finite fields, you can think of basically a system of solutions of a polynomial equation in two variables with coefficients in this finite field fq, for example. Okay, so I think this is one of the things I think every student of Riemann surface theory should see at least. I mean, should know that. And if you want to check, you can go and check. There are many, of course, references for this thing. You can read up with details and all that. Any questions or comments? Okay. So then I will tell you a little bit about also. Oh yeah, something which is really surprising and very beautiful as well, which is this the following fact. So this is how to put it? Maybe I just say algebraicity. I think there should be such a word like this. Algebraicity of Riemann surfaces. Okay, so first of all, so the following theorem is true. I won't prove it because, again, I mean, to do this course well, you have to spend at least a year. So, at least, I said. Oh. Okay, so theorem is the following. Any Riemann surface, any compact Riemann surface, not any Riemann surface, any compact Riemann surface X admits a holomorphic embedding into P1, oh, not P, into P3 of C, the three-dimensional projective space. I mean, sometimes you can embed in P2 in the projective plane, as we did in some cases, but not always, right? But P3 can always arrange. And sometimes, very rarely, but it happens. Sorry, but sometimes even into P3, I mean P2. Well, of course, do you know when this can be embedded in P1 of C? When a Riemann surface can be embedded into P1 of C? When is Riemann sphere? There's only one boring case, which is, I shouldn't say boring, but there's a really absolutely, boring case, P1 of C. But P2 of C, you can get some higher genus scales embeddable into P2 of C. Certainly, some elliptic curves can be, but P3 of C always. You can always arrange for that. Okay. So there is this X, then there is this holomorphic embedding into P3 of C. So f of X is a submanifold, is a Riemann is a Riemann surface of this complex manifold. So it's subcomplex manifold. Okay. So this is not so bad to prove. Actually, maybe I'll prove it on Thursday. But what is really, really interesting is a consequence of this. So this is another fact, which is called Chow's theorem. So that's really beautiful fact. So Chow's theorem says that any actually complex submanifold of Pn is algebraic. I mean, this is really incredible, right? So any complex submanifold, submanifold of Pn of C. So let me put it here, submanifold, say Y of Pn of C is algebraic. So i.e., so by algebraic means the following very simple thing, as you have seen, I'm sure, i.e., there exists a system, actually a finite number of homogeneous polynomials, system of homogeneous polynomials. Basically, I just write P I of, this is n, x0, x1, xn, such that your y, your complex submanifold y, is a set of solutions of this system of homogeneous polynomial equations. So this is kind of also we discussed it in the case of Riemann surfaces to define it using this homogeneous or homogeneous thing. So basically this y is this set of all x0, x1, xn. I mean the classes of this thing. So let me write it homogeneous coordinates such that pi of this x is equal to 0. Now, I here is just a finite number of indices. So, right? And this is P3. This is a special case. So our Riemann surface is a submanifold, complex submanifold of the complex dimension 1 of P3 of C. But the theorem of Chow is very general. Now, so what does it mean? It means that any abstract Riemann surface, there's always a system of equations homogeneous equation that this is the set of solutions of that system of equations. Algebraic equations, that's quite surprising, right? That's quite surprising. So in particular, you just say any, so just the slogan is that any Riemann surface is algebraic. By the way, it is not true that any complex manifold, compact complex manifold of dimension bigger than or equal to 2 is algebraic. By far, it's not true because they don't necessarily admit embedding in the projective space.
So any Riemann surface, not just compact.
Oh, no, any compact. Oh. Thank you, Gabi. Yeah. Any compact. Yes, of course. Oh, I will give you a counterexample right away. Any compact Riemann surface is algebraic. That's what we claim.
Sorry, you said that for complex manifolds,
It's not true.
even if they're compact,
Even if they're compact, there are, it's not difficult actually. There are compact complex manifolds that do not admit embedding in projective space, any projective space. And to prove that, you have to use this results of Hodge decomposition because it enforces some restrictions on this cohomology. So you construct some compact complex manifolds whose cohomology does not satisfy these conditions of Hodge decomposition, so they don't admit embedding.
can you give me an example that embeds into P3 is allowed, P2?
Or embedding of, oh yeah. So yes, it will come actually when I discuss hyperelliptic curves. They are not necessarily always in P2. They have to be, sometimes they will be in P3. Yeah. I will give you an example in later. Yeah. Okay, so yeah. So this is the slogan, and this is a very important thing to bear in mind. That's why in 19th century, Abel and Jacobi, without having a picture of Riemann surface, could do so many things about Riemann surfaces because they were just working with these equations. They didn't know what they were dealing with geometrically, but they were just working with equations, and that's because of this. Actually, that's the reason. Yeah. Right. So, but then let me give you an example of a non-compact which is not algebra. So the Riemann surface. So here is so it's a counterexample. So this is Riemann surface of log function, logarithm. Right. So what is that? So morally, we want to look at y equal to log x. But instead of looking at y equal to log x, we don't know what log is. We look at the surface of x equal to e to the y. X equal to e to the y. I mean, this is very badly defined, but this is always defined. So we just look at x to be the set of all x and y in C2, right? Such that x is equal to e to the y. I mean, this is a smooth condition, so this is a Riemann surface. Easily seen. We did the example. So this is a Riemann surface. So this x admits this function x to C, which is actually the home. This x is really the home of the log function, if you will. The home of the log function is not this strange thing. You cut the line in the plane. It's a pain, and you have to consider the angles, and there are so many cut lines. It's just a mess, right? But this Riemann surface is really the home of the. It's canonical. It's God-given. It's up there. So it's nice. So what is this? Well, the map is you just send pair of x and y to y, which is morally log x without any pain. This is log x, right? Because this satisfies this equation. Now, this is a Riemann surface, non-compact, and is not algebraic. Okay, so x is non-compact and non-algebraic. I think you can prove this even as an exercise. You just write down the equation. You see that the function e to the x cannot satisfy y equal to cannot satisfy an algebraic equation in two variables. I mean, this is you can even. What's that? Yeah, that also would work. Yeah, but I mean, this is x is non-compact and non-algebraic.
It's not compact because it goes up infinity.
Sorry,
It's not compact because it goes up infinity.
that's right. This set as a subset of C2, it has points that are far away from the origin as much as you want. So it goes to infinity. Yes, it's not compact. It's not confined to some bounded part of C.
But what if we pick a different projection map? Instead of projecting onto y, and we picked a different map,
The projection into X,
Yeah.
that's also a holomorphic map.
but that's algebraic.
That's what?
That's algebraic.
No, that's not algebraic. No, that's not an algebraic function. So X is e to the Y.
Right.
That's not an algebraic function either.
Oh.
Yeah, no, this equation cannot be realized. Set of solutions of this equation cannot be realized as set of solutions of polynomial equations in any number of variables. No matter how many equations you take, how many variables, it doesn't. So,
But how do we prove that?
sorry,
How do we prove that?
prove that it's not algebraic?
Yeah.
Oh, right, yeah, by contradiction, write down a polynomial like this and put y equal to e to the x, and you see that you cannot have an algebraic relation between x and y. By taking derivatives and this, I'm pretty sure this is not more than calculus. This it's actually high school. I'm pretty sure it's really high school.
Isn't it because E is transcendental?
Hmm?
Isn't it because E is transcendental?
What do you mean? What you mean? The number is transcendental?
Can we use that?
But that's a very deep fact. But this is easier than that. Yeah, that's a good point. I think that's proving that E is transcendental is who proved it that this is transcendental?
But if we have x equal
I believe
10 to
it
the
was
y
done
plus
by
x.
I believe pi was done by Lindemann. But E, maybe Lindemann, I'm not sure.
But we use different base for the log. Like let's say we use base 10, so x equals 10 to the y,
Yeah.
it's still algebraic.
What?
If x equals 10 to the y, for example,
That's not algebraic.
that's not algebraic.
No, they don't know. Exponential functions or log functions are not algebraic. That's one.
So
Yeah.
E is kind of arbitrary, when it's a different number instead of E. And the
That's right.
ratio instead of-
Yes. Yeah, I don't know who did the transcendence of E. No, check Wikipedia. Whoever did. I know Lindemann did pi. And then this was called in 19th century was called the theorem of the century, which is totally a stupid name because there were many, much more important things were proved in 19th century, including things by Riemann and all the things goes to there. I don't know why this one theorem was singled out as theorem of century.
Elementary prove that pi or E are algebraic or are transcendental.
Or transcendence of pi, you can read it in the, as an appendix in a beautiful book by Spivak, Calculus.
So
He gives the proof. I believe that's the simplification by Hilbert. So Hilbert made a name for himself by giving a more simple proof of the thing. But it's really, again, there's an idea, but it's differential integral calculus. We can actually, yeah, as I said, read it in Spivak's book. He gives the transcendence of both, actually. But irrationality is a different issue. It's much simpler, and that was proved much earlier. Irrationality of E and pi, I believe. I have no idea how this is proved, by the way. Okay, so Chow's theorem we covered. Now we go back to. I wanted to you guys to see these two results because these are kind of important. See these results. So now we go back to our period map and Jacobian of a Riemann surface.
Sorry, we haven't given the example of the density P3 one.
It is coming.
Okay.
It's coming. Yeah. So recall. So the setting was X is a compact Riemann surface, as always. I mean, most of the time for us. And omega of X is the vector space of holomorphic conforms. Holomorphic conforms on X. We know that this is, of course, a complex vector space and its dimension over C is equal to the genus of the curve of the Riemann surface. Equal to genus. And we also looked at H1 of XZ, the singular homology, first homology of X with integral coefficients. This we know is isomorphic to Z to the power 2G. So very abstractly, we define this period map P from H1 of X and Z, right? To omega of X star, the complex dual of this vector space omega of X. So the map was defined like this. If you have a cycle element in the homology on the left-hand side, C, you send it to the following map, to the map that sends a differential one form, holomorphic one form, into its period with respect to C. So this is called the period of omega. Of little omega, sorry. Okay, so then one issue, so we define lambda. This was the notation. Lambda was the image of E. So this is inside. It is an abelian subgroup of omega x star. Right. So one issue was to show that this lambda is of rank 2G, has full rank. So you see, as a complex vector space, this is of course isomorphic non-canonically to CG, and again non-canonically to R, to the 2G. But we really wanted to show that this lambda is a full lattice, is a lattice, is a co-compact lattice in R2G. I mean, because I mean, all of this could go to something of much lower rank, for example. But what is the guarantee, right? So that's the thing. But abstractly we defined Jacobian of X, Jac X, to be omega X star divided by lambda. So this is the Jacobian of X. So this is an example of what something which is called abelian variety. An abelian variety. And I told you that abelian varieties are generalizations of elliptic curves. They are beautiful generalizations of elliptic curves. They generalize elliptic curves. A lot of things you do for elliptic curves, in some cases you can also do for abelian varieties. Curves. So we'll go back to that very soon, but let me now recall how we prove that this is a full lattice. So how we show more or less that lambda is a rank 2G lattice. is a rank 2G lattice. So for this, we just so let me just pick a basis here and pick an arbitrary basis there, and then everything you want to know is reduced to study a G by 2G matrix. Okay, so let me just tell you then what we do. Okay, so fix a basis, any basis you want for now. I mean, basis as a free abelian group. These free abelian groups have basis. It's a free abelian group. C1, I just write C1. I don't put brackets around it, but C1, C2, C2G of H1 of X and Z. And the basis, any basis you want. And the basis omega 1 omega G of omega X, right? Then there is something that we can say is a, we call it period matrix, which is of this form, is a G by 2G matrix, which is consists of these periods here, periods of forms with respect to different cycles, right? So that's what we did. So this is something maybe period matrix for now, but then I will modify this definition a little bit, just a bit, very soon. Period matrix, so it's a G by 2G matrix. Okay, so this G by 2G matrix works like this. For now, there is here G, there is 2G. So the terms say, I don't know, maybe Pij is integral of omega I over cycle Cj, right? Yeah, I by J, right? So I between G and 1, and J between 2G and 1. So then what we did, okay, so but this is a general matrix that here it just appears in Pij's here, which is integral of omega I over Cj's. But it's hard to know something about this, the nature of the lattice, just looking at general basis. But then I said that Riemann chose a very, very particular basis for H1 and very particular basis for omega. So Riemann chose, and this is indeed in his paper, exactly what he did. Riemann chose a symplectic basis. So this symplectic basis is labeled differently now. It's just A1, AG, and B1, BG for H1 of X and Z. So this symplectic basis for H1 of X and Z means the following. I mean, I wrote these relations like this: AI dot AJ is equal to 0 is equal to BI dot BJ, and AI intersection pairing with BJ is delta IJ. So this is intersection pairing thing. So, right? I mean, I described this a couple of times at least, so intersection pairing. Right?
What about AI dot AI? Is that also zero?
AI with what?
AI with AI.
Oh, these are always 0, yeah.
Even when the INJ are the
And
same.
then even INJ are equal, yes. Because if you take a cycle, you want to take intersection with itself, just perturb it a little bit, then it won't intersect. So that's it. That was the idea. I mean, this can be precisely defined in algebraic topology called cap product, I believe. So this is It's a standard thing in singular homology. We can read it in any undergraduate books. So this exists. So this is a basis he chose, and I gave you the geometric meaning of this basis. And for omega i's, he chose the Poincare dual to these things, as I said. So let me just write it here. He chose for omega I. So there was a statement. So there was a lemma that he. I'm not sure we proved this lemma actually, but maybe okay. So lemma there exists the basis of holomorphic one forms. Now omega 1 omega g of omega x such that integral of omega I over aj is actually equal to delta ij. Yeah. I mean, these forms are basically Poincare duals of these cycles, these one forms. I mean, okay. Okay. So now if you use that, then you get something beautiful, because this period matrix looks this looks much simpler in this basis because of this identity relation. Half of the matrix reduces to the identity matrix. In this basis, the period matrix reduces to, okay, so this reduces to this matrix. Okay, so you put A1 up to AGs here and B1 up to BGs over there. And here there's our omega 1, omega G parts. I mean, this is, so there is identity here. 0, 0. And here are these other periods which you don't know what they are. And they contain all the information, these other periods. This integral omega I over bj. So yeah, if you look at this, the picture that we had for this. Okay, I don't know what if you call these things AI. The other ones that go around the other direction around each hole is, this is B1, this is A1, then this is B2, this is A2, and so on. So if you integrate over this, then they define these numbers. And then, so what we proved indeed was Riemann bilinear relations. So this was this needed some more work even. So this Riemann bilinear relations affirms that this matrix, this G by G matrix, so the matrix, so the notation I used is Z, but I'm going to change the notation. I'm going to call it tau, actually. The matrix tau, which is the G by G matrix, consists of all these non-trivial periods, omega I over bj. You see, this Riemann bilinear relations had two parts, you remember. First of all, tau was symmetric. So it shows that tau is a symmetric matrix. So in other words, tau transpose is equal to tau. This is the standard definition of symmetric matrix. And the second property was that the imaginary part of tau is positive definite matrix. So you see, you can write tau because it's a matrix of complex numbers in general as the real part of tau plus I, imaginary part of tau, And this imaginary part of tau. So first part of Riemann binomial, second imaginary part of tau is a positive definite.
What is it? Maybe positive definite?
What's that?
What is positive definite?
I will tell you what it is. It's a positive definite matrix. So I can give you at least 3 definitions of positive definite matrix. One definition is that it's a symmetric matrix, all whose eigenvalues are strictly positive.
Okay.
That's one. The second one is that you can say that this quadratic form is positive definite in the sense that if you just take any matrix like B, tau B, or inner product of B, tau B, is always positive for any B different from 0. There is a third one which says that all these determinant minors from the top left corner to the whole thing are also positive, but one is enough.
Oh.
Yeah. Okay, so that's positive definite matrix. So this is what it is. So then this really shows that. I mean, easily if you think of the definition. So this shows that in this basis, the lattice lambda, the period lattice lambda, the lattice lambda, which I can think of inside R2G, looks like the following thing. So this is a ZG direct sum tau. So I should put here imaginary part of tau. ZG. Okay. Okay. Now we have seen something like this for G equal to 1 before. So consider the case G equal to 1. So this was, so we had the torus. At least we know one example of a Riemann surface of genus 1, which is the tori. X is equal to C divided by lambda. So now lambda is in general of the following form, is omega 1 z, right? Direct sum omega 2 z, right? So if you have a general lattice, you can always, by definition, a general lattice of this form, omega 1, omega 2 are independent over the complex numbers. Oh, no, over real numbers, sorry. Omega 1, omega 2 are 2 complex numbers which are independent over real numbers, okay? So then what happens here is that you can multiply this, obviously, by constant C. By C different from 0 belonging to complex numbers, such that lambda looks like actually, if you go to that basis, lambda is going to look like this. I mean, any lattice basically, after you multiply by this, C lambda is going to look like Z direct sum tau Z, where oh, I should have put here tau. Where this is tau. Yeah, this was a mistake. Here, this is tau. Where image of tau is positive. So this is a kind of a standard way of working with lattices in the complex plane. So there is this 1 here. There's 1, and there is this tau in the upper half plane. So tau belongs to H, which is the upper. I mean, it's called Poincare upper half plane. We come back to that very soon. This is called the upper half plane. Okay. So if you look at this, Okay. So this is this one, and then we have got these other points. So yeah, this is this one of these parallelograms is called this Fourier parallelogram, and these are the two generators. One generator is in the standard form U1, which also we have it in general, but here is tau in the upper half plane. Okay. I mean, tau is imagine part of tau is part. So in general, our lattice then is going to look like this. So in general, lambda is going to be of the form ZG, the sum of tau ZG. That's what Riemann wrote. And things are much, I mean, most probably, I mean, certainly he was aware of this picture and he generalized it to genus G case. So it's a highly non-trivial generalization. So this space is a very important space. Okay, so I mean, immediate corollary is that, I mean, so the Jacobian of X is a compact complex Lie group. Of course, it's always abelian because it is abelian by construction because it's addition. The operation is addition on forms. I mean, this is just omega x star. This is vector addition here divided by lambda. So, but also we know that any compact complex Lie group, holomorphic Lie group is abelian without even knowing beforehand it's abelian. Anyhow, so it's abelian, it's a compact abelian complex as a compact complex abelian Lie group. I mean, topologically, of course, Jacobian, like any quotient that you take, Jacobian of X, of course, is isomorphic to products of circles, S1 cross S1 to G. Is a torus of rank 2G, is a compactly, but that's completely belies the deepness of the situation because this is, if you write it like this, you don't see the holomorphic structure at all. The thing is in this matrix. The juice of the construction is in this matrix, which is a point in the Ziegel upper half plane, upper half space. So this is important. So belongs to, so there is an analog of, so maybe I call it HG. So this is called Ziegel upper half space. Upper half space is the perfect analog of upper half plane, but this is the set of all matrices tau belonging to Mn of C. I mean, I just write the definition again, such that tau is symmetric and imaginary tau is positive definite. Yeah. So this is a non-compact, certainly open subset of Mn of C. So it admits a holomorphic structure also. So I mean, so this space is very important, and I mean, in particular, for any point in this space, we can define one of these abelian varieties. Whether it is Jacobian of something or not, that's another problem, but you can always extend the construction.
So when you say imaginary part of tau is greater than 0, you mean tau?
Sorry.
You mean tau is positive definite, right?
Yes. I mean, imaginary part of tau is positive definite. Yeah, exactly. Yeah. So I extended this notation from real numbers to matrices.
Okay.
Which means symmetric and positive eigenvalues, so strictly positive eigenvalues.
And what's N?
Hmm?
What is N? Is N related to G number?
Oh, yeah, you can say G. Yeah, I'm sorry. Yeah, that's a good point. Yeah. Oh, very good. Yeah. I won't forget your corrections.
Sorry.
Excellent. Very good. Okay, so we take a break, and when I come back, then I will give at least half of the proof of Abel's theorem, because that's now. Yeah. Oh, yeah. Yeah. I still give an example where that curve comes into the picture, and it's also important in general, that example. And then I will discuss the necessary part of Abel's theorem. Okay. Any questions? Hmm?